Hi, everyone, and welcome to the final presentation for the Henrik CS Plus team. I'm Alex, and you'll be hearing from Kevin and Jeffrey later in the presentation. Let's start off by explaining who we are and what we're doing. Our team name is Henrik, which stands for Helping Novices Learn and Debug Relational Queries. This summer, we worked on developing a system called IREX, which is another acronym that stands for Interactive Relational Query Explainer for SQL. In other words, IREX is an interactive SQL query debugger. I mentioned that the R in Henrik stands for relational, so let's briefly talk about what that means. It turns out that today in the era of big data, much of that data is stored in relational databases. The relational data model represents a database as a collection of tables, which are also called relations. Each table stores data in rows and columns. If we want to model a social network, we may have a user table to store information about users. Each row in the user table represents one user, and each column represents various data attributes corresponding to each user, like name or age. In much the same way that relational databases are a very common way to store data, SQL is a nearly ubiquitous query language for accessing data stored in relational databases. SQL queries often follow a select from where syntax, which lets users specify input tables and Boolean conditions on their columns in order to return rows of interest. This is somewhat straightforward to see from the example here, but SQL queries can get pretty complex. This is also a perfectly valid SQL query, but it's very complicated and contains many levels of subqueries nested inside the main query. Note that the whole query is composed of multiple select from where statements in parentheses. As you can imagine, cases like this can make learning SQL a daunting task. With this in mind, we set out to make IREX in order to help students understand complex SQL queries and explore them piece by piece.
Here's what we wanted IREX to be able to do. In this presentation, we'll focus on the tracing features of IREX. We wanted users to be able to understand how input data rows relate to output data rows of a SQL query, and understand when various Boolean conditions on the rows are satisfied or not. Some SQL queries are composed of other queries, called subqueries. You should also be able to navigate between subqueries and trace through each one individually. Although this is not the main point of this presentation, note that we also use small database instances to make tracing easier, rather than showing the full database, which can be very large. These features already worked before the summer for very basic SQL queries, but more work needed to be done in order to support full SQL features. Here is the basic layout of IREX. A allows you to see the query you submitted. B allows you to see what part of a query you are exploring. C gives important context information about other queries that may impact the one you are looking at. D shows you what the input tables are for this query part. E shows you whether or not Boolean conditions are satisfied for the selected input rows. And F shows the output rows from running the current query part. One of the early challenges we faced was getting acquainted with the existing code base. This involved learning new languages and frameworks such as HTML, JavaScript, and Vue.js. Additionally, we found that the existing backend code did not support processing queries that use many of the features of SQL that we need to support. We also needed to spend some time designing new front-end interfaces and interactions for users, depending on how we thought students would want to explore different types of queries. At the same time, we couldn't spend all of our effort on front-end design because we really need to get most features of SQL supported end-to-end, at least for simple cases, in time for the fall 2020 semester, when IREX will be deployed in CS 3.16. Additionally, we submitted IREX to the VLDB conference and got a demo paper accepted, and we need a relatively robust system to present at the conference in late August. So we decided to prioritize getting end-to-end support for features, rather than perfecting front-end designs for the time being. This summer, our progress was mainly refactoring of the front-end code, as well as large changes to the backend to support the types of queries that were previously unimplemented. Concerning code refactoring, our previous front-end code consisted of multiple components all reactively updating upon a state change. The new front-end now consists of one or two components reactively updating to state changes and passing these changes as props to smaller reusable components. Not only does this refactoring help in the organization of the code structure, but the interactions between our various components and our Vuex store is now much more intuitive. Concerning the backend changes, which I will go into more detail in the next slide, but the general idea behind these changes were to support the 3 new types of queries that we are working on implementing. These being subqueries in a from clause, set operations like union, intersect, and accept, and group by, and aggregation queries such as sum or max.
Now we will show IREX being used in action. First, let's take a look at a SFW query that has all the common keywords. We enter the query and click Submit. Below, we can see the database that will be used for this query. Let's click on Debug This to start unraveling this query. This query first performs a left join on the two tables beer and likes. We can explore how each tuple would join with each other by selecting on combinations in the from tables. Any joined combinations of tuples that pass the where condition will be shown in the intermediate table. The join tree displays if the join condition is satisfied. For example, these two tuples don't join together because name Dixie does not match with beer Corona. But if we switch to a different tuple, we see that they do join. This query also has a where condition that filters out beer's name Amstel. So although these two tuples join, they are not displayed in an intermediate table because the where condition is not satisfied. We can also click on intermediate to trace backwards. If we click on the first tuple, we see that it was produced because likes doesn't have a beer named Dixie. So because it is a left join, it joins with nulls. Next, we will look at the aggregation in this query. After joining and filtering, we group the tuples by beer name. The yellow represents the columns in the groups, which can be seen above. This aggregation table is nested, and each group contains its relevant tuples. For example, Corona has two tuples in its groups, and it's also seen here in intermediate. The aggregation table also includes any aggregation present in this having and select parts of the query. So here count is shown for both. Finally, we take care of the having condition, which keeps only groups with count greater than 1. So only Corona appears here in the final output. If we click on the other groups, we see that they have count equal to 1 and therefore not pass the having condition.
Here I will be showing the implementation of subqueries in the from clause. Our example query will find the beers liked by at least one person who frequents bars named alphabetically larger than J. The final output are the beers Amstel and Corona. In the from tables section, we can see a table named JD, which was the name that we gave our subquery. The tuples shown in the JD table are the output formed by the subquery. We can confirm this in two ways. We can either click into the subquery by using the context nav like so, and see the final output here, or we can use a drill down function by clicking on the magnifying glass in the table itself, like so.
The set operation interface is a little bit different than for other queries. We still have the input tables and output table, but there aren't any intermediate results. Instead, when a set of rows is selected, we give a brief explanation of how the relevant input rows contribute to the output row. Then we can go into the subquery context to understand how the Q1 and Q2 input tables get their results. These subquery contexts look basically the same as they would if we ran these queries individually.
Auxiliary feature we implemented was being able to easily customize the database that we are running the query on. Sometimes tracing a query can be better understood if tuples are deleted or inserted. Thus, this will allow users to interactively see how tuples are executed in concert with each other. In the future, we plan to add more features that corroborate the understanding of SQL queries, such as natural language and hints that lead the user towards the right query. These are all research questions that will take a great undertaking in achieving. Although we've come a long way this summer, we still want to support even more SQL constructs. We hope to roll out IREX and Duke's CompSci 316 Intro to Databases course in the fall 2020 semester and assess how effective it is at helping students understand SQL. In previous semesters, CompSci 316 instructors used a tool like IREX to help students debug relational algebra queries, which are much simpler than SQL. However, this tool did not allow for tracing through query results like IREX does, so we're interested in how much benefit this new functionality provides. We will construct interactive tutorials and example queries for students to understand how to use this tool. Thanks for watching our presentation. At this time, we're happy to take any questions.